Welcome back, everyone. This is Dan from the Rensselaer Polytechnic Institute Engineering Ambassadors, and in this video, we're going to continue talking about 3D printing and how you can use it in the engineering design process. But this time, we're actually going to use it to do something. This is the second module in our 3D printing and engineering design video series, and today I'm going to give you your first engineering design challenge. You will have to design a vehicle so that the drag force on it is as small as possible. Today, we will learn about drag force, and you'll design your own aerodynamic vehicle in Tinkercad and load it up to 3D print. After it is printed, you'll test your print in our wind tunnel to see just how aerodynamic it is. I'm sure almost all of you have stuck your hand out of a moving car window at some point and felt some sort of resistance, but what you probably didn't know is that this is an example of drag force. What you are feeling when you do this is a force against your hand pushing it back as the car moves forward, and this is the drag force. Drag force is caused by air molecules hitting your hand and transferring their energy. In the next section, I'm going to use the word fluid a few times. Normally when we say fluid, we mean a liquid like water or soda, but in engineering and science, fluid means anything you can easily move through, so that means liquids and gases. And now that we've cleared up what a fluid is, drag is the force that opposes motion through a fluid. The equation shown here is how we calculate the drag force for an object moving through a fluid. It has a lot of different components, but once we break it down, it will make sense. In the equation, the FD stands for drag force. So all the equation is saying is 1/2 times V squared times P times A times CD equals the drag force. This funny looking P is the Greek letter rho, and it is a symbol for density, which is a measurement of how thick a fluid is. More specifically, it is a measure of how much stuff is within a given volume of a material. For example, water and air are both fluids, but water is more dense, so it is harder to move through. V stands for velocity, which is simply the speed and direction of the object. If the object is stationary, then the V also stands for the wind speed. The A stands for area, which is how big the object is when you look at it from the front. And finally, CD is the coefficient of drag, which is a constant attributed to the shape of the object we're looking at. In this video, we will see an important consequence of drag force. These skydivers are wearing wingsuits, which are like parachutes, and they increase the area of the skydiver to slow users down as they fall. This larger area increases drag, so they can essentially fly over the city. Now we're going to go into why engineers might want to study drag and devote so much time and money to understand it. Any projectile flying through the air is encountering a drag force. The fluid, whether it be air or water, slows down the projectile. The projectile could be anything from golf balls, footballs, and baseballs to planes or missiles. No matter what it is, the drag force will cause a decrease in velocity and change the trajectory of the object. Here's an example of how a bicyclist tries to limit the drag force that acts on him. As you can see, he is hunched over. This is beneficial because it reduces his frontal area, which in turn reduces the drag force. One important consequence of drag force is fuel consumption. Fuel consumption is a function of engine efficiency and power. Power is a function of the drag force and velocity. Therefore, fuel consumption is a function of engine efficiency, drag, and velocity. If we hold the engine efficiency and velocity as constants and increase the drag, then the fuel consumption increases. This is an important problem for engineers. Obviously, as fuel consumption increases, so do your costs. In addition, there isn't an unlimited supply of fuel resources, so it's important to be conservative. Shape is an important aspect of drag force. Shape 1 has a very flat, boxy surface, so this shape would have a very high drag coefficient. Shape 2 has a curved surface, so its drag coefficient would be smaller than Shape 1. Shape 3 has a very slim curved surface, so its drag coefficient would be smaller than both Shape 1 and Shape 2. These cars have similar frontal views to the shapes we just looked at, and we can see that these shapes greatly affect the CD of the car. Engineers have a process to design a vehicle or object with the least amount of drag possible. This process usually starts out with a CAD model of the vehicle in a program like Tinkercad. Engineers want to measure drag, and there are two ways to do this, with a simulation and a wind tunnel. Shape is one of the most important components of drag, so engineers try to figure out how they can change the shape or the frontal area of the vehicle to limit the drag. After a CAD model is created, a first step in determining the drag on an object is to use a computational fluid dynamics, or CFD, simulation, which is what this video is going to show. This simulation will provide a number for the drag coefficient that engineers can use in their calculations. The next step could be to test a small-scale model of the object in a wind tunnel to calculate a real-world value for the drag coefficient. This model could even be 3D printed as a rapid prototype, and we're going to do that in this module. Finally, the finished product can be tested in a wind tunnel to make sure that numbers from the previous tests were accurate. The lines you see above help engineers see how the air is flowing around the car, and these are produced by coating wires in oil and heating them up so that they produce smoke. Now that you know the basics behind drag force, all of you are going to act as engineers who are trying to design a vehicle, and it can be any vehicle, a car, a plane, a rocket, to have the least amount of drag possible. You are going to design a model of your vehicle in Tinkercad, and these will be 3D printed when you're done. Then, you use our wind tunnel to figure out the drag coefficient of your model. The goal is to have the smallest drag coefficient possible. Unfortunately, your design does have to have a maximum size so that it can fit in the wind tunnel and fit on the printer's build plate. It also has to have a minimum size because we want to pretend that people could fit inside the vehicle to operate it. The dimensions are shown here, so your design must be smaller than the top row and bigger than the bottom row. Now, I'll open up Tinkercad to show you some tips.